Hey guys, how you doing? It's Coach Scott, and we're getting ready to start our unit that's after the Christmas break, and we're going to be talking about states of matter, or states of matter. So let me get my little pen so we can move this thing forward like so. So we've studied atoms, and we know more now than what we did when we started, and we know that atoms are the basic unit of stuff, right? And again, what is matter? Matter is stuff. So when we look at the nanoscale, at the atomic level, we know that atoms are bound together and they bond together to create compounds due to what? The electronegativity and the Coulombic or the electrostatic attraction. Now, chemical compounds are going to react with each other, and they'll break and then they'll reform bonds, and when they do, they'll make new chemicals, right? So here's an example. I've got two water molecules, right? This little dotted line right there, that little dotted line right there. Let me get to where I've got a little pen here. All right. Okay, so anyway, you got these little dotted lines. That means there's an intermolecular attraction to each other. And one of those waters will pull the hydrogen off and create hydronium, H3O plus, okay, and then it'll become hydroxide. So we also know what? That atoms and molecules are very small, all right? They're on the nanoscale. We can't see these substances because it's made up of so many of these particles. So I've got 1 milliliter of water at 4 degrees Celsius is going to equal 1 gram of water. And then, check this out, 1 gram of water has 3.34 times 10 to the 22nd molecules. That's 3 with 22 digits after it. That's a lot of molecules in a small little container, right? So what makes all these water molecules stick together to make them the liquid water we're used to when we drink? All right, that make them where we can actually see them. Let me get over here and move this thing down. Maybe, yeah, there we go. So it's out of the way. Okay. So what have we learned so far? Okay, we know that atoms and elements. We know how we can explain atoms, we explain the elements, and we can talk about the periodic table and how they're set up according to the quantum numbers. Then we talked about molecules, how the atoms will come together and form molecules. All right, and those are the most common way we're going to find atoms in nature. And then we learned how these atoms from the molecules will rearrange in chemical reactions to form new chemical compounds. All right. The molecular compounds, the ionic compounds. Now we're going to study these intermolecular forces that occur between molecules to create the common states of matter. So intermolecular forces are the pieces we need to add to the puzzle to explain the world, right? To explain stuff. Without these intermolecular forces, you wouldn't have tables, a lake, the ocean, walls, even us. So these intermolecular forces are important, and they shape the world as we know it. So there are many states of matter, but there's 3 common ones that we're going to see and that dominate the world, and they're what? Gases, liquids, and solids. Now, there's some more exotic states, some weird states like plasma, nuclear matter. We're not going to really get into that. So there are 2 fundamental differences between the states of matter, liquid, solid, and gas. The distance between the particles and the particles' freedom to move. All right, so gases, they're far apart, the particles, the molecules, the atoms, what have you. There's total freedom. They can move wherever they need to go. And most of what makes up of gas is empty space. And there's total disorder. And the name for that is entropy. We'll get into that later. Now, as I cool or I increase the pressure of a gas, I can create a liquid, which still has disorder, but there's some freedom to move around relative to each other, and they're closer together. Now, if I heat or decrease the pressure, I can go from a liquid to a gas. Okay? If I heat or whatever. Now, a crystalline solid, all right, is very ordered. All right? The particles are in a fixed position. They're very close to each other. These are the solids that we're used to seeing. Now, we're going to watch a video about the phases of matter. The phases of matter. So hopefully this will work. And I'm going to pause. And here we go.
So I wanted to talk to people about the different states of matter, solid, liquid, and gas, using water as an example. But I thought first I better be sure that we're all on the same page about what water is made of. What's water made of?
Water?
Yeah. What makes water?
Water.
Okay, what elements does it take to make water?
H2O.
So what does that mean?
It is water.
What elements? Water and cold. Water plus cold.
But what does the H and the O mean?
Something in oxygen.
Something in oxygen.
Hydrogen.
There you go.
Hydrogen.
Hydrogen and oxygen. What's the 2 mean?
Hydrogen, oxygen.
And the 2, H2O. Why do we say 2?
I don't know.
It's 2 particles of hydrogen and 1 of oxygen.
There you go. So that makes what we call a water compound. two atoms of hydrogen and 1 atom of oxygen makes a water molecule.
Molecule.
I know, the word was like on the tip of your tongue. I guess we got there in the end. So what's the difference between solid and liquid water?
So obviously the temperature of it. It's a lot colder.
Ice is frozen.
What does it mean to be frozen then?
Cold.
Liquid water is no good for skating on. Ice is great. Yeah.
Nothing other than temperature.
So everyone recognizes that temperature is important in determining whether the water is ice or liquid. But what's actually happening between the water molecules? What's the difference between water and ice?
It's frozen.
What does it mean for something to be frozen?
It's solid.
And what does it mean for something to be solid?
That it's like a brick.
It's like a brick. And what makes it like a brick? What's happening in there?
I don't know.
But what makes it a solid versus a liquid?
Well, in this case, lots of pipes going underneath. But
That makes it very cold.
makes it very, very cold. Yeah.
But what's actually happening to the little bits of water?
They're attaching to each other. They're attaching to. I mean, this is all the guesswork here. I imagine they're attaching to each other. They're forming a more solid interpiece.
You cool liquid water down, and then at some point, what happens to it?
I don't know, it slows down, freezes, and stops moving.
The molecules become frozen.
How do they become frozen?
They join together. They accumulate. They coagulate.
Coagulate is not the technical term for it, but everyone was on the right track. In ice, the water molecules are basically fixed in place. They form a crystal lattice, where their only motion is vibrating. So what happens if we heat up the ice? What happens when, a solid melts?
They all bounce out and
What are we talking about?
melt.
What is they? What are they doing?
Well, like in science, you draw little circles.
What are those little circles?
Oxygen.
Are they just oxygen?
Hydrogen, oxygen. And the 2.
And the 2.
The temperature is higher.
So the particles, they're less stable.
Yeah.
Less stable?
Not stable.
More free to move around.
That sounds right.
They become separate and they are allowed to move around. And in gas, maybe they're further apart. Is that what we're okay?
This is
yeah,
fantastic.
That
This
makes
guy's
sense.
nailed it.
All right, that makes sense.
That's
now.
awesome.
All right.
So in liquid water, the water molecules not only vibrate, they can also rotate and slide past each other. And this is what allows the substance to flow. At even higher temperatures, the water molecules become free of that liquid and turn into water vapor. In that state, they are very, very far apart and moving very quickly. So the major differences between solid, liquid, and gas are the motion of the particles and the distance between them. Of course, you may want to meditate on these differences some more. What about the difference between a solid, a liquid, and a gas?
Oh, that's easy. I teach meditation, and it's all about as you de-excite something, so you de-excite the mind, you get more orderliness. As you de-excite water vapor, you get water. As you de-excite water, you get ice. More orderly. So in fact, the molecular structure becomes more orderly. That's the difference.
That sounds quite reasonable. How do you de-excite something?
Well, in this case, you actually remove energy from it. In human beings, you calm their minds down with meditation.
And that works.
It
We
does.
get de-excited.
Yeah.
Does that mean if I meditate too much, I might turn into ice, though?
No, but you'll generally become cool.
Good answer, sir. Thank you so much.
Well, you guys know more about that right now than most of those folks from Australia. I think they were from Australia. So, anyway, a gas will assume the shape of its container because it's moving around freely. The volume, the gases will expand its volume of that container. So, if I've got a bottle of gas, it's all in that bottle. It's very compressible because most of a gas, the molecules of a gas, the volume is empty space. It flows very easily, all right? And it's got a very rapid in its diffusion. A liquid will assume the shape of the container of the part that it occupies, so it can flow. It's got some freedom. It will not expand its volume of the container. It will only take up the volume of the liquid. It's virtually incompressible because there's not a lot of free space in between the molecule. It flows easily, and it's got a much slower diffusion rate than gas. Okay, a solid. It will retain its own shape regardless of what the container is. It will not expand its volume to fill the container. All right. It's virtually incompressible. There is no space, hardly, between those molecules. All they're going to do is vibrate. They do not flow. A rock will not flow. And it's got the slowest rate of diffusion. So, the solid and the liquid states, the particles are extremely close together, or we say they're condensed, and we call these the condensed phases. Again, the liquid, there's some freedom, but they're relatively close to each other. In a crystalline solid, the particles are in a fixed position. All they're going to do is vibrate. So those are what we call the condensed phases. Now, which of the following is the characteristics of a gas? Well, it takes on the shape of the entire container. We know that, so that would be C. Which is the following is the characteristic of a liquid? Take a moment and think. Pause. Well, that would be A. All right. It will fill only a portion of its container. It's not compressible. It does not take the shape of the whole container. What is the following as the characteristics of a solid? Take a pause. Of course, that would be B. The molecules are in relatively rigid positions, and it is. Okay, now let's go into intermolecular forces. We've been talking about there's something holding those molecules together, right? Not the atoms in the molecule, but the molecules themselves. So, the state of a substance at a particular temperature and pressure depends on two major factors. Number one is the strength of the intermolecular forces that hold these molecules together. Second is the kinetic energy of the molecules. Now, a solid, all right, there's not a lot of kinetic energy there. They're in a nice orderly pattern. In a liquid, the molecules can move about. All right, in a gas, they're moving all everywhere. They're bouncing it against the sides of the container, against each other. They're just moving around freely in space. So which of these would have the highest kinetic energy? Pause. And of course, that would be gas because they're constantly moving. They're moving quickly. Yeah, so they've got a lot of energy there. So intermolecular forces are the electrostatic attractions or repulsions that exist between the molecule. All right. The attractions are between the molecules, not inside the molecules. All right. This is the intermolecular force. That's a relatively weak force compared to the intramolecular covalent bond that are holding those compounds together. All right. So that's the biggest difference. So a chemical bond is what? Well, that would be B, right? B, because it is an electrostatic force of attraction. Which the following correctly ranks electrostatic forces from weakest to strongest? Try that for just a second, and I'll tell you. Pause. Well, the ionic bond is the strongest one because it's a positive negative, almost magnetic, but it's electrostatic attraction between an anion and an ion. The answer is B. The covalent bond is a little weaker, all right? That's where they're sharing the electrons, and of course the intermolecular force, which we're going to be learning about over the next couple of weeks, is the weakest. Okay, so that would be B. Which of the following is pointing to an intermolecular bond? Well, we got A there, intermolecular. B is pointing to those little dots right there. Then we got C, the OH bond. That's an OH bond, and that's an OH bond. So, of course, that would be, pause, hopefully you said B, because that is the intermolecular bond. Which area is pointing to what? This area is pointing to what? Well, it wouldn't be A and B because it's not. It is a intramolecular bond. Ooh, intra. That's not an ionic bond. That is a covalent bond, so that would be A. Be the most correct answer. Okay. So without the IMFs, or those intermolecular forces, and I'm going to start saying IMF from here on out. All right. All substances would behave like an ideal gas. There would be no liquids or solids. We wouldn't be here. The molecules would just be moving around freely, right? No friction, totally just elastic off each other, off the sides of a container, right? So we can't do this anymore because, well, Flash is dead. But temperature is directly proportional to the average kinetic energy of the molecules that make up the substance. So temperature is a measure of the kinetic energy. And we're going to get into this concept greatly over the next couple of months. So what is boiling? Boiling is a transition from a liquid to a gas. And in order to make that transition, molecules in the liquid must break free of the intermolecular forces that are holding them together. We're going to find out what those intermolecular forces are. So, the kinetic energy of the molecules is proportional to the temperature. When we measure the temperature, we're measuring the amount of energy involved there, the kinetic energy. So when kinetic energy arises, so does the temperature. So boiling point refers to the temperature at which the molecule's energy will overcome the IMF binding them together. And the higher the boiling point of a substance, the stronger the IMF. So the higher the boiling point, the higher the force holding it together. Water has got a relatively high boiling point at 100 degrees C. So there's a very strong IMF holding it together. So intermolecular forces are strongest in what? Pause, and that would be A, solids, because they are being held together, right? A substance boils when the kinetic energy of its molecules what? Overcomes the intermolecular forces bonding them together. Not always 100 degrees C. For water, that's true. Okay. And that's it for this video. All right, so we're going into a really cool part of chemistry that we're studying. And this is getting into the physical chemistry part of it, the physics of it, of how we can overcome those forces. So I think we'll have fun with it. So you guys, this is Coach Scott. Hopefully everybody had a good break. And so deuces for now.